and welcome to this lecture. So far we've been looking at independence of two random variables, and we saw quite a few examples and calculations involving that. Now we're going to naturally move from 2 to 3 and 4 and higher numbers. So let's look at how to think of independence for more than two random variables. Okay, so here's the definition. Definition itself is quite okay. I'm not being very precise. I've just vaguely said what it is. It's sort of an extension of the independence for two random variables, right? So if you have n random variables and you want to say when they are going to be independent, if you basically define events with any subset of them which are different, and then those events have to be independent, right? An easier way to think of independence in the discrete case is this formula. Okay, so you take the PMF, the joint PMF of all the n random variables. These are all discrete, so it's easy to write it down like that. It has to factor into the product of the marginals. Okay, so it's a simple enough criteria. Once you get something like this, then everything else follows in the independence. Okay, so this criteria, hopefully you see the extension from the two random variable case, right? fxy of fxy became fx times fy. fx1 through xn simply becomes fx1 times fx2 till fxn. It's a natural definition. Once again, a joint PMF equals product of the marginals, conditional PMF equals unconditional PMFs, right? So you can forget about the conditioning if you condition anything within that. If you take a subset of the random variables that are independent, they are independent. And you will see quickly how independent random variables are very, very easy to work with. Anytime you have probabilities involving each individual random variable, you can multiply the probabilities together, and the PMFs multiply like this with no conditioning, etc. It's very, very easy to work with. Okay. So let's see an example. As usual, we jump immediately into an example. This is our familiar tossing a fair coin thrice example. We know the joint PMF has 8 different possibilities. Every possibility is with a value of 1 by 8, right? So you can see that each xi, if you find the marginal, we have done this before, it's basically uniform 0, 1. The marginal is also very easy to write down, and you can very easily check that for every t1, t2, t3, the joint PMF 1 by 8 equals the product of the marginals, half into half into half. Okay, so clearly everything is independent here. It works out very easily. Okay, so this is how you determine independence from joint PMF. Okay, but of course not all joint PMFs will result in independent end up being in a situation where the random variables are independent, right? Here is another example that we've been seeing so far. You have a 3-digit number, and I define these 3 random variables. X is the first or the 1000th digit, right? 100th place digit. So I'm sorry, 100th place digit. X is the first digit from the left. Y is the number modulo 2. Okay, so it's 0 or 1. If the number itself is even, then y is 0. If the number is odd, y is 1. And then z is the first digit from the right, the units place digit. Okay, so we saw that the marginal distributions are all uniform here, right? X is uniform from 0 to 9, y is uniform 0 to 1, and then z is uniform 0 to 9. Okay, but now let's look at independence of pairs of random variables first, right? So x and z, you will see, are independent. Okay, so you can quickly check. I'm not going into the detailed calculation here. I will leave these as exercises for you. Please check this. The joint PMF of x and z alone will be 1 by 100. Okay, so you can check, I mean, it's easy to calculate the probability that x equals 0 and z equals 0. You'll see it's 1 by 100, and that's exactly the product of the marginals, isn't it? 1 by 10 into 1 by 10, you get that the equality satisfied. So x and z are independent. Likewise, you can show x and y are also independent. But if you look at y and z, you will see that they are not independent. Okay, once again, remember, how do you check something is not independent? You just have to find one counter example, one t1, t2, such that the fxy of t1, t2 is not equal to the product of the marginals. Okay, so here is one example I've given. Y equals 1 and z equals 2. So notice what happens here. If y is 1, then the number has to be odd. And if z is 2, the number is even. So those two together are never going to happen, right? So fxy of fyz of 1, 2 is actually equal to 0. On the other hand, the product of the marginals will work out to be 1 by 2 into 1 by 10, which is 1 by 20. So in this case, you have this problem that 1 by 20 is not equal to 0 clearly. So this is not independent. Okay, so you notice how this is working out. 1 and 2 can never happen together, but 1 can happen by itself, 2 can happen by itself. Right? There's no problem there, but 1 and 2 cannot happen together. Okay, so this is how you check that y and z are not independent. So if y and z are not independent, clearly x, y and z are also not independent. Okay, so that's a not independent case. Okay, so these are dependent random variables. Okay, here's another example which I'm going to call even parity. So here is a joint PMF for you. F x1, x2, x3, x1, x2, x3 take 4 possible values together: 0, 0, 0, 0, 1, 1, 1, 0, 1 and 1, 1, 1. Okay, so there's a mistake here. This has got to be even parity. So this is 1, 1, 0. I've made a mistake here. 1, 1, 0. The reason why it's called even parity is in every case the number of ones that are there in x1, x2, x3 is even. Okay, so this is just a name for the thing, but you can see why this. So you can once again check independence in this case. Okay, so here what will happen is if you take any pair of x1 and x2, okay, x1 and x2 will be independent, x2 and x3 will be independent, x1 and x3 will also be independent. Okay, so you have 3 random variables here. Contrast with the previous case, right? The previous case you had x, y, z. We saw y and z were not independent. Okay, so clearly all 3 are not independent. Look at how interesting this case is. In this case, x1 and x2 are independent, x2 and x3 are independent, x1 and x3 are also independent. You can check individually, right? You can see, if you just look at x1 and x2, you have 0, 0, 0, 1, 1, 0, 1, 1 occurring each with 1 by 4. That's independent, isn't it? We know that. x1 and x3, again 0, 0, 0, 1, 1, 1 and 1, 0. Again, I made a mistake here. I made a typo here. This is also independent. And then if you look at x2 and x3 together, you again get 0, 0, 1, 1, 0, 1, 1, 0. Again, all 4 possibilities, 1 by 4 probability each. So all pairs of random variables are independent, but the 3 random variables together are not independent. They are dependent. Why is that? You can look at the case 0, 0, 1, which does not appear in this table, which means the probability of those 3 occurring is 0, isn't it? 0, 0, 1 is 0. Okay, but the product of the marginals will work out to half into half into half, 1 by 8. So this is a violation of the condition that's needed. So all 3 together are dependent, but pairwise they are independent. So this will happen always with for the even parity case. Why is that? If you think about it, if you look at all 3 together, you can find x3 given x1 and x2. Okay, so x1 and x2 will fully determine what exactly x3 has to be. So in all those cases you have dependencies. Okay, so that's what's important. Okay, so this is an example. So I'm just trying to show you examples of how dependency and independent can occur in so many different guises. So you have to be very careful and look at the formula carefully to check if it is dependent or independent. Okay. Now the easiest case is the so-called IID case, and it's very common and it occurs in so many situations, and we often use what is called this IID case, independent and identically distributed case. You have any number of random variables, but if they are IID, then you are in a good situation because you can do a lot of calculations easily. I hope to convince you of that in the rest of the slides. But let's look at the definition first. Okay, n random variables are said to be independent and identically distributed if, first of all, they all have to be independent, and then the marginal PMFs are identical. Okay, so the joint PMF, right? So what will happen to the joint PMF? You can see if they are independent, the joint PMF is product of the marginals, and the marginals are all identical. So you just take one of the marginals, raise it to the power n, you will get the joint PMFs. Okay, so everything is easy in the independent and identical case. IID case is very easy. So basically, why does it occur often in practice? So often when you do statistics in real life, you have to imagine some trial gets repeated over and over again, and you want to sort of assume that the distribution is identical every time it's repeated. Only then, only when it repeats like that, you can hope to gain some information from it. If every time something very random happens, you can't do much about it, right? So you have to assume that the same experiment, repeated trials are coming up if you want to pick up something. So that's why this happens all the time. So you saw these Bernoulli trials that we saw before, right? And again, you're assuming the same situation gets repeated again and again. So independent and identical often happens in practice. I've given you a few examples. So we'll use this notation in particular. Well, I'll use this very simple notation. I'll say x1, x2, xn, IIDX. Okay, so if I say this, what does this mean? IIDX. There's first of all a random variable x with PMF fx. Okay, so there is some random variable x with PMF fx. Okay, so that's the distribution, that's the common distribution here. And these n random variables x1, x2, xn, they are all IID according to the same distribution of x. Okay, so they all will have the same marginals, and the marginal will be the marginal of x. Okay, so that's the way to think of this notation. So it's just a convenient notation. So I might also sometimes say, or I might also say like this. Okay, x1, x2. When I don't want to use this random variable x, I might say IID fx. Okay, so give the PMF itself. Okay, so these are convenient shorthand notations to describe what the distribution of n IID random variables is. Okay, so once again, this is an important definition. It will happen, it will show up again and again when we look at statistical scenarios. Okay, so let's jump into one such statistical scenario and then see if we can do a probability calculation. I assured you in the IID case, many calculations are easy because the random variables are independent, events defined with them are independent, so you can multiply probabilities together, everything becomes easy. So let's take a few problems, one problem at least to begin with, and see how we can do it. Okay, so here there are n random variables x1 to xn. They are IID with geometric p distribution. Right, so you remember the geometric p distribution, right? So what is geometric p? Geometric p, it takes values 0, 1, 2, so on. And what is the probability here? Probability of success, I'm sorry, it starts with 1, I keep forgetting that. Okay, starts with 1, 2, 3, and so on. Okay, the random variable takes 1 with probability p, it takes value 2 with probability 1 minus p times p, it takes probability p 3 with 1 minus p squared p, so on. Okay, so probability that x equals k is 1 minus p power k minus 1 times p, right? So x is geometric. Okay. All right. So the question that is asked is, what is the probability that all of these random variables are larger than some positive integer j? Okay. So the question that's being asked is, what's the probability that x1 is greater than j, comma x2 is greater than. Remember, what is comma? Comma in this case is and. Okay, all the way till xn greater than j. Okay, so normally you might say you'll have to look at the joint PMF and look at all the favorable cases and add the probabilities of all that and all that you might have to say. But remember, this is IID, so these are all independent random variables. So when they are independent, the events defined with them are also independent. So you just simply write it as probability of x1 greater than j times probability of x2 greater than j. You can take product of these probabilities and you will work out. Not only that, these are all now identical. x1 to xn are identical. They are distributed the same as this x here, which is geometric. So all of them are equal and equal to this probability j, and then if you multiply it n times, this just this guy raised to the power n. Look at how easy it is, right? So I'm defining some complicated condition involving n random variables. Just because they are IID, it just simply reduces to this case. So what is probability that x is greater than j? It's 1 minus p power, so maybe I'll just write it like this, summation k equals j plus 1 to infinity 1 minus p power k minus 1 times p. So this is a geometric sequence with the first term being 1 minus p power j by j divided by 1 minus p, and that is just 1 minus p power j. Okay. So this using this back here, you will just get 1 minus p power j times n. Okay, so it's as easy as that. Okay, so look at how easily we got to the answer using this property that it's independent and identically distributed. Okay. So here's another question, what would seemingly be slightly complicated, but once again you'll see the independence assumption gives you the answer quite easily, but this one involves slightly more involved calculation. So let's see if we can do this, okay. So here is a random variable x, and the distribution, I like to write the distribution like this. I think it's a very compact way of representing distributions in the general case instead of doing tables. So x takes values 0, 1, 2, 3, 4. 0 with probability half, 1 with probability 1 by 4, 2 with probability 1 by 8, 3 with probability 1 by 16, 4 with probability 1 by 16. And x1 to xn is being said basically this is IID samples with distribution x, so IID x, so that's what this is saying. So what's the probability? That 4 is missing in the sample. So the first question asks me probability that x1 is not equal to 4, comma x2 is not equal to 4, so on till xn is not equal to 4. What is this going to be? If it were something else, we would be totally confused, but this is IID, isn't it? So IID is simply, I know that this is probability that x is not equal to 4 raised to the power n, right? So I don't even have to go through the complicated steps of coming to this. I know this is always true. So what is probability that x is not equal to 4? It's 1 minus probability that x is equal to 4. So that just works out to 15 by 16 raised to the power n. See how easy it was to get to this answer, okay? Let's look at next one. What's the probability that 4 appears exactly once, okay? Now this is a little bit more confusing because 4 could appear in x1 and not appear elsewhere, or it could appear in x2 and not appear elsewhere. Like that there are multiple possibilities, right? So this one is a little bit more 4 appears once, appears exactly once, right? So this exactly once is needs more cases. This is probability that x1 equals 4, x2 not equal to 4 till xn not equal to 4, or disjointly, or x1 is not equal to 4, x2 is 4, x3 is not equal to 4, dot dot dot, xn is not equal to 4. Likewise, it can keep on going till the last case where x1 is not equal to 4, so on till xn minus 1 is not equal to 4, and then xn is equal to 4. So luckily, you know, every term here in this summation has the same value. And what is that value? This is just you know, n times, there are n terms here, n times probability that x is equal to 4 times probability that x is not equal to 4 raised to the power n minus 1, isn't it? So you can see when every term is probability that x equal to 4 times probability that x is not equal to 4 raised to the power n minus 1. And how many terms do I have? N of them. Notice how independent and analytically distributed helps you. So this is n times 1 by 16 times 15 by 16 raised to the power n minus 1. Okay, so it sort of looks interesting. Okay. There are so many other ways to do this very quickly if you want to. You can do, I mean, you can see that it will be a binomial and do this very easily. So what is the probability that 3 and 4 appear at least once in the samples? Okay, so now we have to do a little bit more thinking. There are multiple ways to do this problem. Once again, you can write it as, you know, the intersection of two events, and then you can do various things with it. But let's try and repeat this method. 3 and 4 have to appear at least once, right? So this at least once complicates matters, right? If it were to appear exactly once, then you can do some calculation like this, but this is at least once, okay? So whenever it's at least once, 3 could appear once, 3 could appear twice, 4 could appear once, 4 could appear twice. It looks like all sorts of possibilities are there. So it's a little bit more twisted. So P is 3 at least once, okay, intersect 4 at least once. Okay. So how do we go about doing this? So one of the things that is easy to calculate here is 3 at least once. Okay, so let me call this event A, this event B. So it turns out probability of A complement is easy to find. What is A complement? 3 3 never appears, right? So 3 appears at least once. A complement is 3 never appears. Now that's easy, we have seen this before. It's 1 minus probability of C, that's 15 by 16 power n. Likewise, this is also, you can find probability of B complement. 4 at least once complement is 4 never appears. So that's also 15 by 16 power n. Okay. So I need A intersect B, right? A intersect B is A complement union B complement, the whole complement, right? So I need to find probability of A complement union B complement, for which I need A complement intersect B complement. Okay, so I'll find probability of A complement intersect B complement. What is A complement intersect B complement? Think about this. This will happen if 3 should not appear and 4 should not appear. Okay, so 3 should not appear and 4 should not appear. And if you think about it, this will be 14 by 16 raised to the power n. Okay, so think about why this is true. So each x1 is cannot belong to 3 comma 4. X2 cannot belong to 3 comma 4, like that, right? So it's probability that x is not equal to 3 or 4 raised to the power n, and that is 14 by 16. X should be 0 or 1 or 2, and that's 14 by 16. So this gives you probability that A complement union B complement is what? This plus this minus this, isn't it? So it's 2 into 15 by 16 power n minus 14 by 16 power n, and then you have probability of A intersect B, which is A complement union B complement whole complement, that's 1 minus, right, 2 times 15 by 16 power n minus 14 by 16 power n. Okay, so I mean, I had quite a few reasons why I put this problem out. It's a bit of a difficult problem. It's not very easy, particularly the third part. But I wanted to convince you that even though you might think once you come to PMFs and CDFs and random variables, you can forget all about the basic probability. Notice how basic probability is coming in and helping you. So, right, the good understanding of the axioms, writing events in terms of letters, right, from translating the English description of the events into A and B and then manipulating it with unions and intersections and complements really helps you solve problems, right? So how we got to a complicated problem like 3 and 4 appear at least once in the samples, it seems like a complicated calculation, but if you break it down into what it is and then write it as A and B, and then go to A or B and then use the knots in the middle and write the intersections and complements and go back and forth, magically you get to the correct answer. Okay, so hopefully at least part 1 and 2 are very simple. The part 3 is a little bit more complicated. Maybe there are other ways to do it which are interesting to you. I will welcome you to try it, but this is one way in which you can use the axioms carefully and you get to the answer. Okay. So anyway, the moral of the story is, in most cases when you have IID scenarios, you can calculate probabilities like this without too much trouble by using basic ideas. Okay. So the next problem that I would like to do in this area of independence and all that is this wonderful property of the geometric PDF. It's this so-called memoryless property. Let's see it as a problem and solve it. Okay. So the first thing is something we have seen before. What's the probability that x is greater than n when x is geometric? It's just simply summation k equals n plus 1 to infinity. I just did it just now, but let's see it once again. This is 1 minus p power n times p plus 1 minus p power n plus 1 times p plus so on. This is a geometric series with common ratio 1 minus p, and the first term is 1 minus p power n times p. So you do 1 minus p, you'll simply get 1 minus p power n. Okay, so that's what this is. Now the second question is asking you to find probability that x is greater than m plus n given x is greater than m. Okay. Now this this is a conditional probability. So conditional probability is P of A given B is P of A intersect B, right, divided by P of B, isn't it? What is x greater than m plus n intersect x greater than m? Both have to be satisfied, which means that is just x greater than m plus n, isn't it? So x needs to be greater than m plus n and x needs to be greater than m. I mean, if it's greater than m plus n, it's already greater than m, so you don't need to have that. other condition. So you can see the intersection is actually the greater of the two, right? So x is greater than m plus n. So now you've reached this nice formula. So notice this 1 minus p power m plus n divided by 1 minus p power m, which is once again 1 minus p power n. Okay. So this kind of a relationship, right? So probability that, so that implies, look at this, let me just box it up. X greater than m plus n given x is greater than m is equal to probability that x is greater than n. So this is called a memoryless property of the geometric PDF. Okay. Remember, what is geometric distribution? You keep tossing a coin. What's the number of tosses needed to get the first head, right? So that's the geometric PMF. What this tells you is, given that there are like 1,000 tosses for which you did not get heads, okay, and then you ask what's the probability that you have to wait for another 100, is exactly the same as starting at the 0th toss and asking what's the probability that you'll have to wait for 100 tosses to see the first head. Okay, so that's the sort of memorylessness property. Whatever happened so far is irrelevant. Given that I'm here, given that already so many have passed, you still see the same distribution for the future. Okay, so that's called the memoryless property of geometric. It's worth remembering. This is a pretty famous property. How do you use these properties? So for instance, in a real scenario, you may want to model some random occurrence. And when would you go to geometric? When you observe a property like this. No matter how long you've been observing something, if the probability that, if the distribution that it's going to take, the event is going to take beyond that point is the same as always, then you know it's like a geometric. Maybe geometric is a good model. Okay. So we'll stop here with independence and independence of multiple random variables and IID and all that, and move on to the next topic in the next lecture.